Hello. Hey, everyone. Okay. Can people hear me? See something in the chat? Okay, good. Right. So I hope you enjoyed the last assignment, which was due this Sunday. And we are off into the new topic. The new topic is, well, it's energy work and conservation of energy, of course, and power. So today we're going to talk about all of these. And without any further ado, let's dive into it. I've got some amazing questions today. Okay. Right. Well, first of all, I just want to remind you of the work energy principle. Basically, if you do work on an object, you change the energy of that object. Yes, but the thing is, the work energy principle is written in different ways. Depending on the book you have in front of you. Okay. So I'll just find the chat. Chat, yes. Here it is. So I like the simple version. I like the simple version of the work energy principle. Work energy principle. That the change in kinetic energy of an object is equal to the work done on that object. That's a very simple way of putting it. Okay. You do work to change the kinetic energy of something. Okay. Imagine you take a ball, like a tennis ball, and you throw it. When you throw it, you do work on that tennis ball. And as you do work on the tennis ball, the kinetic energy increases. So the change in kinetic energy is equal to the work done. Right. Example, do work on a tennis ball. To increase kinetic energy. Sometimes work is negative. Yeah, for example, if you want to stop a tennis ball, you catch it in your hands. In this case, you're doing a negative amount of work. You're doing negative work to create a negative change in kinetic energy, so a decrease, okay? To increase kinetic energy, right. Just so if the ball is moving this way, a distance s, and the force is F. So the work is force times distance times cosine 0 degrees, right? So that's going to be a positive value. And if the ball is moving this way, but the force is the opposite way, so the angle between them is 180 degrees. So work is force times distance times cosine 180. And cosine 180 is -1, so that's going to be negative. Okay, so force, so increase. That means the change in kinetic energy is positive. You're increasing the kinetic energy of the ball, and here your change in kinetic energy is negative. So you're decreasing the kinetic energy because the work is negative. Okay, makes sense? Type a number 0 to 10. How much sense does this make so far? Okay, love it. Good. All right, and of course, what makes conservation of energy super exciting and super interesting is when you mix it with conservation of momentum. So let's have a look at a very simple question, which to me, when I studied physics at roughly your age, maybe a bit earlier, I was like, okay, so if you take a rifle and you shoot from the rifle, the momentum of the bullet and the momentum of the recoiling gun have to be the same, because conservation of momentum. But how come the bullet has so much more destructive power than the recoiling rifle? Because I mean, the momentum is the same, but the rifle doesn't do nearly as much damage as the bullet does. So let's have a look. So we have a toy gun, of course, which shoots a bullet. And the speed of the bullet is, let's say, v. And the speed of the gun is u. The mass of the gun is m capital, and the mass of the bullet is that. Now, ignoring the signs, positive and negative, we know that the momentum is the same. So mu is equal to mv. Yeah, by modulus. By modulus means we are ignoring the signs. We're going to square the velocity anyway, so it doesn't really matter what we do. Okay, that means we can express u as m over m capital V. Right. So basically what it says that the velocity of the rifle is a fraction of the velocity of the bullet, and the fraction is equal to the ratio of the masses. Okay. Let's find the kinetic energy then. Kinetic energy of the kinetic energy 1 of the rifle is 1/2 mu squared. And kinetic energy of the bullet is 1/2 mv squared. Now, if I substitute, so that is equal to 1/2 multiplied by m multiplied by m over m squared v squared. Now I can find the ratio of the kinetic energy of the bullet to the kinetic energy of the rifle is 1/2 mv squared divided by 1/2 m over m squared v squared. So that cancels, 1/2 cancels. You're left with, so m and m squared cancel. This also cancels, it's going to be m over m. So the ratio of kinetic energies is like this. Basically, if the rifle is 100 times heavier, kinetic energy, its kinetic energy is 100 times smaller. Okay, so kinetic energy of the bullet is equal to m over m of the kinetic energy of the rifle. That means the kinetic energy of the rifle is very, very small. Therefore, it has less destructive power. Okay, and that's why the heavier the rifle, the better. And also, what you do when you shoot, you put the rifle against your shoulder, and that effectively makes you and the rifle one whole thing. So it's a massive thing. Therefore, and this reduces the kinetic energy of the rifle even further because you hold it and you and the rifle become one. So you don't take the mass of the rifle, you take the mass of you and the rifle. Therefore, the even further reducing the kinetic energy of the recoil. Okay. Right. So does that, any questions? Any questions? Okay. So the heavier it is, the less kinetic energy it will have in an explosion. Also, yes, if you let's think of an explosion, for example, a supernova explosion. When a supernova explodes, a supernova is a massive star at the end of its life. It explodes into small pieces. Supernova, nova, explosion. And the smaller the piece, the more kinetic energy it has. Funnily enough, yeah, smaller pieces have more kinetic energy than more massive pieces. Smaller debris are likely to have more kinetic energy. And that's why we get things like gold. You probably know that all the gold that you have ever seen, all the gold that exists on Earth are debris of supernova explosions. For example, I have a gold ring on my finger. So it was once in the center of a supernova explosion. And then it fell as a, I don't know, maybe it was a debris from which the Earth was formed, or perhaps it was a meteor strike containing gold which hit the planet Earth, and somewhere in Siberia they found the gold and made a ring out of it. I'm always fascinated by these things. Okay. Problem 2. A boy mass of 50 kilograms is standing on a stationary skateboard on a smooth surface. He throws the ball of mass 10 grams at a speed 10 meters per second relative to the ground. Find the change in kinetic energy of the ball. Okay, so that's easy. A boy mass standing on a stationary skateboard on a smooth surface. All right, so a boy is on a skateboard. And he is throwing a ball of mass 10 grams. So 10 grams at a speed of 10 meters per second. 10 grams, 10 meters per second. And find the changing kinetic energy of the ball. Oh, well, that's easy. Change in kinetic energy is equal to 1/2 mv squared. So it's a half times m, which is 0.01 times v times 10 squared. And that's 0.5 joules. Have I made a mistake? No, I haven't. So half a joule. So the boy throws a ball, and the kinetic energy of the ball is 0.5 joules. Now, same boy, but traveling at 10 meters per second on a skateboard. This is the kinetic energy paradox, which was in the assignment, which is in the assignment. So the boy is already moving at 10 meters per second. And he throws the ball at 10 meters per second. That means the ball is now moving at 20 meters per second. So the change in kinetic energy of the ball is 1/2 mv squared minus 1/2 mu squared. So it's the final velocity minus the initial velocity. So that's 1/2 times 0.01 times 20 squared minus 1/2 times 0.01 times 10 squared. And that is 400. There's 4 divided by 2. That's 2 minus 0.5, 1.5 joules. I don't know if you see the issue here. It's the same boy using the same muscles, throwing the ball at the same speed, because in the frame of reference of the boy, he's throwing the ball at 10 meters per second. Like, imagine this was in a closed railway car, and you don't know how fast it is traveling. You throw the ball the same way, there's no difference. Okay, Newton's first law was very clear on that. If you're moving at a constant speed, there's no difference of how yes, all physical law, so all laws of physics are the same in every inertial frame of reference. And yet, if you're standing still and you're throwing a ball, you're creating does that mean that as the Earth rotates, it gain much more energy? I don't see how this is related to this situation. So this is bizarre. Sorry, do you understand the issue here? Do you understand that there is a problem? That we're doing the same muscles are doing the same amount of work and yet creating a different change in kinetic energy? Type yes or no. Okay. So yes, so this is known as the kinetic energy paradox. When you are looking at different, from the point of view, a different frame of references, kinetic energy paradox. The boy does the same amount of work yet produces a different change in kinetic energy. So because there's no friction, there's no external forces, but we are given the mass of the boy. Work is force times distance. Sam, you're onto something. Yeah. because it's the same force acting over a bigger distance. This is one way to resolve this paradox. So as a matter of fact, it's if you look from the point of view of a stationary observer, the boy throws the ball, but as the boy throws the ball is already traveling 10. So the ball is traveling a bigger distance. So S is bigger. So work, in fact, is not the same for a stationary observer. The boy does different amounts of a different amount of work in both cases, and it has to be like that. So the amount of work done depends on the frame of reference you're looking where you're looking from. So yeah, that I'm wondering, can we resolve it this way? I wonder if the calculation is going to be harder or easier. Okay, well, anyways, in the first case, the boy rolls back, and the boy is the boy is 50 kilograms divided by 0.01. The boy is 5,000 times. The boy is 5,000 times heavier than the ball. Therefore, if the kinetic energy of the ball is 0.5 joules, the kinetic energy of the boy in the first case is going to be 0.5 divided by 5,000, which is like nothing. 0.5 divided by 5,000. 1 times 10 to the minus 4 joules. Now, in the second case, the kinetic energy of the boy, so this is the change in kinetic energy of the boy. Now here, the change in kinetic energy of the boy is going to be changing kinetic energy of the boy is going to be well, we need to find the final speed of the boy. All right, so we have mass of the boy multiplied by the initial velocity plus mass of the ball times the initial velocity is equal to mass of the boy times the final velocity of the boy plus mass of the ball times the final velocity of the ball. So velocity of the boy is equal to mu plus mu minus m velocity of the ball divided by mass of the boy. So let's have a look. So m50 times 10 plus 0.01 times 10 minus m, which is 0.01 times 20 divided by m, which is 50. So the velocity of the boy is 50 times 10. So 500. Well, we don't need that. Okay, 500 minus 0.01 times 10 divided by 50. So this is going to be 9,998 meters per second. The change in kinetic energy of the buoy is equal to 1/2 multiplied by 50 multiplied by 10 squared minus 1/2 multiplied by 50 multiplied by 9.998 squared. And that 0.5 times 50 times open bracket 100 minus 9.998 squared sorry, I got the same answer, which is bizarre. Apologies. What went wrong? So 0.5 times 50 times 100, 2,500, 0.5 times 50 times 9.998 squared. Yeah, what was the issue here? Okay, yes, so the kinetic energy, the change in kinetic energy of the buoy is one joule, effectively, 1 joule. And as you can see, here, because you have, oh yes, now I see the problem. So in the first case, the change in kinetic energy is nothing. It's like 1 times 10 to the minus 4 joule. So the buoy is not really changing his kinetic energy. Okay, so you can see here, this is no change. Effectively no change, because 0.0001 joule is nothing. Yes, compared to the kinetic energy of the ball. But when the buoy is moving, the change in kinetic energy is 1 joule. It's more significant. Is 1 joule, and this is the extra joule of energy that goes into the ball. Okay, so what we have found, that when the buoy is stationary, he throws it, he rolls back, but this kinetic energy is nothing, because there's a tiny change in in velocity, tiny change in kinetic energy. But as the boy rolls at a significant speed, like say 10 meters per second, it's a significant speed, and he throws the ball, he slows down a tiny bit, but that's tiny change in kinetic energy, tiny change in velocity produces a much bigger change in kinetic energy. Therefore, the boy loses 1 joule of kinetic energy, and that 1 joule of energy goes to the ball. So we have resolved the paradox. So it's not a paradox if it can't be resolved. Okay, make sense? Where's my chat? You could also say that the boy, another argument here, a different argument, different argument. As when you throw the ball moves some distance. So this is the hand of the boy, and this is the ball. And as you, when you apply the force, F, you move a certain distance, S. So work is equal force times S. So this is when you're stationary. But when you are moving, and a stationary observer is looking at you, not only the ball is moving, but your hand is moving. So your hand is moving. Let's draw the final position of the hand. So in this case, your hand goes from here to here. But if you're on a skateboard, your hand goes from here all over to here. So that's S1, and this is S2. So S2 is the distance you throw the ball plus the distance you yourself have traveled. So the force is applied over a bigger distance. So the work is force times S2. It's the same force applied over a bigger distance moving. So same force applied over a longer distance. So in conclusion, the amount of work done by the same force is different in different frames of reference. And a very good example of that would be, imagine you are holding something heavy and you're in a lift. So from your point of view, you're applying a force. This is a Harry Potter mug, of course, obviously, as you would. So you're applying a force, and the force is upwards, but am I doing work? Am I doing work? No. Now imagine I was in a moving lift, sorry. If I was in a moving lift, I'm holding the cup and I'm moving upwards, therefore I am doing work. So from my point of view, I'm not doing work even if I'm standing in an elevator, because in a lift, because it's not, the cup is not moving. But to a stationary observer who's looking at me, they think I am doing work, and that's the resolution of the paradox. So yes, thank you, Sam, for the wonderful idea. I don't know if that was what you were thinking, but yeah, if this was your thinking. Good. All right, so problem 3. Oh, I love this one. A car of mass 1,000 kilograms is stationary. The engine delivers full power of 1,000 brake horsepower. 1 brake horsepower is 740 watts. Friction coefficient is 0.8. Find the initial acceleration of the car. Right. Find the initial acceleration of the car. So let's do it. Let's do it. We know that the power is force times velocity. Okay, so you've learned this formula in school. You should have at least. Power is force times velocity. Sorry, just a second. Okay. And that is equal to the change to the right. Power is, and that's equal to the rate of change of kinetic energy. So it's the change of kinetic energy divided by change of time. Sorry, just a second. I lost the train of thought here. Okay, so yeah, sorry, we don't need that formula. That's why. Right, so we have the change in kinetic energy is equal to the power of the engine multiplied by time. Okay, so I hope you will agree with that formula. So 1/2 mv squared is equal to pt. So from here you can find v. Speed of the car is equal to 2 power times time divided by m, and the square root. No, we need the acceleration. So acceleration is, so we found velocity as a function of time. Velocity as a function of time because you can, well, yeah, that's the velocity. And acceleration is the derivative with respect to time. So that would be, so 2p over m multiplied by 1/2 times t to the power minus 1/2. In other words, that's going to be square root of p over 2t. So what's the initial acceleration according to this? Velocity at time t. And this is acceleration. time t. It is. Well done. It is undefined. But how can it be undefined? A car has acceleration. It can't be undefined. It looks like when t is 0, acceleration is infinite. Let's confirm that. Let's sketch the graph of v. The graph of v versus time is pt. So it's 2p over m. These are constants. The power is constant, m is constant, t is well, square root of t. So the graph is going to be like this. It does look like, because acceleration is the gradient. Acceleration is the gradient. And at this point, when t is 0, the gradient is infinite. But that's impossible. You can't have infinite acceleration, right? That would be instant death to all the passengers. Infinite acceleration. That means infinite speed, infinite force. Yeah, if acceleration is infinite, force is infinite, because force is ma. And if there's infinite force, there's nothing can withstand infinite force. So every time a car accelerates from standstill, the passengers are turned into mush. So that doesn't seem right. So what's going on here? Where did we go wrong? What were the assumptions made? No energy is lost. Exactly, Alexandra. Oh, Alexandra. So assuming yes, the wheels will spin, and some of the power of the engine would be turned would go into turning the wheels into mush. Yeah. Rather than the passengers. So the wheels will spin. There will be smoke coming out of the wheels. That's a lot of thermal energy. So that is plus thermal. And the question has a much easier solution. We know that when a car accelerates, the force that accelerates the car. So if it's a 4-wheel drive car, that means that there's a force here and here, and the F equals ma. The only forward force is friction, and the friction is equal to mu mg. Well, it's a 4-wheel drive car. It's mu mg over 2. So there's front wheels and back wheels. So therefore, acceleration is well, yeah, I'll leave it. Mu mg over 2. So ma is equal to mu mg. Therefore, mass cancels, and acceleration is mu g. And this is the maximum acceleration of any car except for the rocket cars. So there are cars with rockets installed. If it's a wheel-driven car, this is the top acceleration of any car, max. This is when the wheels spin. and this is the maximum acceleration the car can produce, the engine can produce. So no matter how powerful the engine is, we don't even need to know the power of the engine in this particular case. We know the acceleration. So in this case, acceleration is mu g, which is 0.8 times 10, which is 8 meters per second squared. And when it's a two-wheel drive car, well, there's no force on the back wheels, so only the front wheels are producing the force, and therefore, so that's the four-wheel drive car. If it's a two-wheel drive car, then F is equal to MA is equal to mu mg over 2, and mass cancels. Acceleration is mu g over 2, and in this case is 0, so that's 4 meters per second squared. As I said before several times, you're always limited by the wheels and the tires. That's why it's very important to use to never go over the limit with your tires. Okay. Yes, if the wheels have no thread on them, that's very dangerous. There's no grip. You can't really turn properly. You can't really do much about it. Okay, so the initial acceleration is going to be constant, as you can see, because mu g is a constant, does not depend on time. So if you draw the acceleration versus time, if you draw this acceleration versus time, if you sketch this, you would think that it's like this, but it can't be. So basically, this is the equation of the graph. This is the acceleration versus time. And at first, the wheels would be spinning. And whilst the wheels are spinning, your acceleration is like this, is constant. The acceleration is equal to mu g. And then acceleration will decrease according to this law. Okay, so this is proportional to 1 over square root of t. This is how the acceleration changes. And as for the velocity, it doesn't go like this. It goes like this. So you have a constant acceleration, and then like this. And this is one of the questions. This is where the wheel stops spinning. You need to find this time, and then you need to work out this graph, right? So you will actually need to say that velocity of time is mu g t up to when t is less than a certain value, and it's equal to that square root of 2pt over m when t is greater than such and such. So you need to find this t. So this is what you will need to do in the assignment. Okay. To power the car. This is one of my favorite questions. I love it because there's so many things to consider. Any questions? So spinning, rolling, and the same thing here. Any questions? No. Good. Right, next. A So a puck of mass 1 kilogram is sliding across a table when it encounters an unattached wedge of mass 5 kilograms. The height of the wedge is 1.2 meters. There is no friction. The initial speed of the puck is 5 meters per second. Find the final speed of the puck and the wedge. So what do you need to consider here? What are the things to consider? Come on, just help me. You use your microphone. Yes, conservation of energy. And in what way? So what do you need to check? Or what are the possible scenarios? What are the possible scenarios? Yes. What is the GPE at the top to determine whether it will go over or not? GPE at the top is equal to MGH. MGH, that's equal to 1 times 10 times H, which is 1.2, which is 12 joules. Okay, what's the kinetic energy initial kinetic energy? So it's 1/2 mv squared, which is 1/2 times 1 times 5 squared. So that's 12.5 joules. So will it go over? Is there a possibility that we haven't considered something? Yes, the wedge can move. So as the puck is moving on to the wedge, yes, there's a reaction force here. The wedge is pushing the puck backwards, so the puck is slowing down. But on the other hand, the puck is pushing the wedge this way, therefore accelerating the wedge. So the wedge will also move. So when the puck is at the top, the wedge will move together with the puck. Just one more second. Oh, yes, I see. We basically what we need to do is to find the kinetic energy of the wedge. But we can't really do that just from the data that we have. So what we can do is say, what would the kinetic energy, what would the kinetic energy, of the wedge be if the puck was traveling at the minimum speed required to go over the wedge. Okay, so what would happen then? Well, I will tell you what would happen. You would see the wedge and the puck on top traveling at the same speed. Let's call it u. The puck, the puck on top of wedge traveling at the same speed. And now we can use the conservation of momentum. Momentum is equal to, so mv0, that's the speed of the puck before, is equal to mu plus mu. So v0, so yes, and then energy. So the energy of the puck, 1/2 mv0 squared, is equal to, so this is the initial velocity, v0, is equal to the mgh plus 1/2 mu squared plus 1/2 mu squared. Okay. What can we do here? Well, we can make u the subject from here. Make u the subject. U is equal to mv0 divided by m plus m. Plug that into here and multiplied by 2 as well. Just mv0 squared is equal to 2 mgh plus 1/2. Oh no, there's no 1/2 plus m squared v0 squared divided by m plus m squared plus 1 plus m squared. What am I doing? We can combine the two. You can see that this is m plus m. So these two can be combined together. So it's m plus m multiplied by m squared v0 squared divided by m plus m squared. So this cancels. We multiplied by m plus m. So yes, m plus m mv0 squared is equal to 2 mgh m plus m plus m squared v0 squared, and v0 squared is equal to V0 squared is m plus m squared minus m squared. Okay, that's better. What am I doing? Like this. V0 squared is equal to 2mgh m plus m. M cancels. You have V0 is equal to square root of 2gh m plus m. All right, let's find that. So it's 20 times 1.2 times 20 times 1.2 times 6. 12 meters per second. Let's see if that makes sense. U is equal to m, which is 1 times 12 divided by m plus m, which is 6, 2 meters per second. Okay, yes. So if this is the minimum speed required, to move the wedge. So just a second. So if the wedge is moving at 2 meters per second, 0.5 times 5 times 4, 10 joules. Yes, the kinetic energy of the wedge would be 10 joules. So if the puck had enough kinetic energy to go over, had just enough, they would be moving at 2 meters per second, with the wedge having 10 joules of kinetic energy, and the puck would be 1 times 4 is 2. Puck would have 2 joules. Okay, yes, would have 2 joules of kinetic energy and 12 joules of gravitational potential, and 12 joules of GP. Therefore, the conclusion oh yes, you're right. Sorry. That might change the outcome. Divided by 5, but by m capital. 2gh. Yes. So 2 times 10 times 6 divided by 5. 4.8 4.89. 4.89 meters per second. 4.9. 4.9 meters per second. Therefore, yes, sorry. The puck has enough. Therefore, the puck has enough kinetic energy to go over. That changes things. Thank you. Thank you, Alexander. Right. So that doesn't make sense. No, doesn't make sense. So checking 4.9 over 6. So that's would be 0.82 meters per second. That's reasonable. So they would be moving at a speed of 0.82. Right. So we have established that it has enough energy to go over, and that makes life easier, because what happens is, first the wedge accelerates, but then as the wedge goes down, it decelerates. Okay, and therefore after the wedge goes down, after the puck goes down, the wedge would stop, and the puck would continue traveling at 5 meters per second. So the answer, velocity of the wedge is 0. Velocity of the puck is the velocity of the puck is 5 meters per second. Now, if they didn't go over, this would be a different story. So proof. Yes, I haven't. I've given you the answer, but I haven't proved it. So proof. And the proof is here. We have momentum. So we have mv0 plus 0. There's no the wedge has no momentum at the start, is equal to mv1 plus m, let's call it v2. The kinetic energy, so 1/2 mv0 squared is equal to 1/2 mv1 squared plus 1/2 mv2 squared. So from here, I can say from here that v0 is equal to, well, yeah, v0 is mv1 plus mv2 divided by m. So it's v1 plus m over m v2. I plug this into here. So 1/2 m multiplied by v1 squared plus 2 v1 m over m2 v2 plus m squared over m squared v2 squared is equal to 1/2 mv1 squared plus 1/2 mv2 squared. Right, so what can we do here? Well, we can cancel 1/2 m, surely. Oh, no, sorry, we can't. That's capital M. We can cancel 1/2. Makes life slightly easier. Open the brackets. So m v1 squared plus, so m2, that's just m. That's plus 2 m, capital M, v1 v2 plus m squared over m v2 squared is equal to m v1 squared plus m v2 squared. So this cancels. V2 V2 open brackets. Oh, I can multiply by m. So 2m m v1 v2 plus m squared v2 equals m v2 squared. We can check that we can check the consistency with the units. So it's m times m, kilograms, meters per second. So the units are consistent. That's good. That doesn't always happen. So v2, open bracket, 2m m v1 plus m squared v2 minus m v2, and that's equal to 0. So either v2 is equal to 0 or v2 is equal to 2m v1 divided by m squared minus m. The capital M cancels, and we have 2m v1 divided by m minus m. So we have the two possibilities. Now, well, I mean, here it is. Here's the solution. This is one of the options. This is when it goes. This is go over, and this one is when it doesn't go over. So this is when the wedge doesn't go over. So what happens here is we have that the puck tries to go over the wedge, but doesn't, and then they travel in opposite directions. We have the puck going left at a speed of v1, sorry, and this one moves forward with velocity v2. Okay, so this is these are the two scenarios. I'll leave this for yourself to prove. Just try prove this yourself, that these are the two scenarios. Prove by yourself. Yeah, and it's quite an exciting thing to do. Right, problem 5, a common mistake. A hairdryer pushes cold air which leaves at velocity 20 meters a second. So you have a hairdryer and it pushes air at velocity 20 meters per second. And the force, the recoil force that you feel is 2 newtons. 2 newtons. So perhaps you can install a Newton meter and that will measure the force of the hairdryer. And yes. Okay. Hairdryer. By the way, if you never mind, it's fine. I just wanted to say it's worth investing in a good hairdryer because a good hairdryer drives your hair in 20 seconds and a bad hairdryer takes ages. So go for the expensive one. You won't regret it. Anyways, have a hairdryer that the air goes at 90 miles an hour. That's really fun to do. 90 mile per hour hairdryer. Anyways, 20 meters per second. It's about 70. Is it 70 miles an hour? No, that's not 70 miles an hour. That's 44 miles per hour. Anyways, 2 newtons, that's the force. And you can be tempted to say, well, the power is force times velocity. And this is tempting. But this formula only works if velocity is constant, which it is not. The velocity of the air is not constant. It goes from 0 to v. Velocity of air, not constant. Therefore, you cannot use this formula. So what you need to do is say, well, the change in momentum, momentum of the air, So the change in momentum is u, and the force is the change in momentum divided by time. So it's mu divided by t. And the power is equal to the work divided by time. So it's the change in kinetic energy divided by time. So it's 1/2 mu squared divided by t. And mu from here, mu is equal to ft. You can substitute that into here. We have from here, we have that the power is 1/2 multiplied by ft multiplied by u divided by t. T cancels and we have 1/2 fu. So it's not that, but that. You can argue that because the initial velocity is 0, the final velocity is v, then the average velocity is half v. That would normally work if you have a uniform acceleration. But what I'm trying to say, don't assume that you can use this formula. Velocity has to be constant. And here you get power, which is 1/2 multiplied by 2 times 20, which is something like 20 watts. And yeah, 20 watts is not a lot. It doesn't sound like a lot, but the fan doesn't produce much power. The power is produced by the heater. The heater uses way more power than the fan. Okay. A jet ski is traveling at speed v. The water is ejected at a speed u relative to the jet ski. Find the efficiency of the engine. So this is quite an unusual problem. You would probably not encounter anything like that in school. So what do you do here? Right. So you need to see what's going on here. So you have a boat or a jet ski. It's a jet ski. It's a thing. It's a thing on water. And here it has a pump that takes in the water at the front, takes in the water. So the water comes in, it goes through a system of pipes, goes through a propeller, and it's pushed out at a speed u. But that is speed relative to the jet ski. Speed relative to the jet ski. Find the efficiency of that, which considered useful energy power in this case. Well, the useful energy power would be force times the velocity of the boat. So the useful power would be the force produced by the engine times the velocity of the jet ski. Right. Now, from the point of in the frame of reference of the frame of reference of the boat, the water comes in, so the boat is stationary. The boat is stationary, and water comes in at a velocity v, because that's the speed of the boat, and water comes out at a velocity u. Okay, so the change in momentum of the water is equal to mass of the water u minus v. Now, if you look at the same from the frame of reference of the stationary water, frame of reference of the stationary water. So first, the water is stationary. V is 0. The initial velocity is 0. And the final velocity, well, if it's u relative to the boat, that means it's moving at velocity, the speed of the jet minus the speed of the boat, u minus v. This is the speed of this stream of the stream of the water coming from the back. And the change in momentum of water is the mass times u minus v, which is the same thing. So that's good. That's good. We're on track. The change in momentum. Right. So impulse delivered by engine, and that is the impulse is equal to force multiplied by time. And the force is the useful power, divided by the velocity of the boat, and multiplied by change in time. And we know that the impulse has to be equal to the change in momentum of the water. So it's m u minus v. So the useful power is m u minus v, mv u minus v divided by delta t. The total power is the change in kinetic energy of the water divided by delta t, because the water changes the kinetic energy. The boat does not change kinetic energy, and so that's equal to 1/2 of the water, 1/2 m u squared minus 1/2 mv squared divided by delta t. Because from the frame of reference of the boat, the water is coming in at velocity v and coming out at velocity u. So the change in kinetic energy is this. So that's equal to 1/2 m u squared minus v squared divided by delta t. And now we find the efficiency. Efficiency is the Greek letter eta, and it's a useful divided by total power. So it's mv u minus v delta t divided by 1/2 m u squared minus v squared divided by delta t. Delta t cancels, m cancels. So what are we left with? We have v u plus u minus v, divided by 2. So 2, this 2 goes up. And then you have u squared minus v squared, which is u minus v, u plus v. You cancel that, and you have the efficiency of the engine is 2v divided by u plus v. And interestingly enough, if u equals v, the efficiency is going to be 1. Yeah. So if the boat is traveling at the same velocity as the jet is coming out of the back of the boat, the efficiency is going to be 1. So it's going to be 100% efficient. 100% efficient. Okay, now I would love to go through problem 7. Let's have a look at what do we have left. So the task is due, the assignment is due, what, 12th? Is it due 19th of March or the 12th? Can somebody remind me, please? Do we have an extra week? 19th. So we have 1, 2. Okay, we have a spare week to do this. This is a long problem. This is a long problem, and I want to go through it properly. So we'll do it next week or the week after. This is one of the problems from the assignment as well. All right, so yes. So I hope this was useful. So this problem 7 is interesting in a way that it's pretty much unsolvable if you're trying to use laws of motion. So you have to use energy to solve for acceleration. So which is unusual. How do you? It's not normal to try to solve for acceleration, for example, using energy. That's not what we used to. But sometimes you do need that. So we'll come back to this question, and yes, have a lovely evening, and I'll see you next week. Okay, bye.